I have the pleasure of introducing Dr. Xiangyu Hu. He completed his PhD in Beijing Institute of Technology, 1999, then went on to make a postdoctoral work in Beijing, Singapore, and Dresden in Germany. He stayed in Dresden, but in the Technical University at Munich from 2006. And he's been a member of the SPH steering committee since 2008. And since then, I can safely assure he's been one of the best known SPH experts in the world. He's kindly organized one of these meetings a couple of years ago in Munich. I had the pleasure to attend to it. It was great. And I think he's going to talk about a very important topic nowadays, not just in the field of SPH all over the place, which is FSI, which stands for Fluid Structure Interaction. And he'll tell you about it, but it's basically just the problem, well, just the very basic problem of describing the interaction between fluids and structures. And it's at the heart of current development in applied engineering and physics, and it's one of the hottest topics all over the place. So without more delay, I'm giving Xiangyu the microphone. And so whenever, right.
Yeah.
Okay, so it's all yours. I'm muting myself.
Thank you. Yeah, thank you very much, Daniel, for the very friendly introduction. Now, my talk is basically on the SPH modeling of flow structure interaction. So I separate this lecture into two parts. The first part, I would like give the basic formulation, which show how we can use SPH to model fluid and solid structure in a unified formulation. And that's the basic formulation. And in the second part of the lecture, I would like to give a little bit more advanced situation, like the case when we want to introduce multi-resolution in this flow structure interaction modeling. So that's the second part. Okay, so let's go to the first part, the basic formulation for SPH modeling of flow structure interaction. So the outline of my lecture is like this. I first would like to introduce the flow structure interaction, basically FSI. It is and its applications in natural phenomena and engineering system. And I'd like to also briefly review those difficulties for numerical modeling of FSI problem. And then I'd like to provide the basic SPH formulation, which can handle this problem, including I would like to introduce a governing equation, and I would like to introduce the discretization for fluid and solid dynamics, and also the discretization of how fluid and structure can be coupled. And at the last, I would like to give some numerical examples to show these applications. So fluid structure interaction is a very typical problem which involving both fluid and structures. And this type of problem can be found everywhere. And in natural phenomena, we can find this problem like in bird flying or fish swimming, or inside our human body with our circulation system, like the respiration and cardiovascular system. Basically, they all related with typical flow structure interaction problems. Certainly, this type of problem is also very popular in engineering system, including many applications like flow, the external flow problems, which we have a structure interaction with external flow, and the structure can also interact with internal flow like combustion engines, and in many environmental flows, which flow structure interaction is also quite important. For example, when we consider wind blowing a bridge, this kind of situations. So the flow structure interaction problem is a very popular topic to do. So to model FSI problem, there's many different approach, but no matter what approach it is, they should be considered the fundamental problem of this, how to couple between the computational fluid dynamics and the computational solid dynamics. So coupling between the two is the fundamental requirement of this modeling problems. So there is a typical approaches, because this problem is already aware by the community for a very long time. So people have developed very different approach. So originally people may use a very classic approach like finite element method or arbitrary Lagrangian Eulerian approach to do the simulation of this problem. One typical issue for those type of method is they basically all rely on a mesh. So there's a so-called mesh method. So mesh method face some really crucial difficulties on modeling this type of problem, because mesh itself introduce a prescribed topology. As just showed in Daniel's lecture, say then the partition, the mesh have a property of partition the space, but with this partition, but they also lead to some other very strong drawbacks because for the lack of flexibilities. So because when you consider a flow structure interaction problem, very often we will face the topology changes. This is including because including the solid and the fluid, and the solid structure very often they have a larger deformation. Then in that case, they will lead to singularities, especially mesh singularities in the mesh. So in that case, there's a topology issue where give this simulation have very bad situation, because it's very easy to lose numerical stability. This issue is due to the problem itself have a topology changes or very large deformation due to the structure motion and oscillation of the fluid. But at the same time, the mesh itself have their own topologies. So this topology can sometimes is not consistent with the topology change of the structures. So that's make this numerical difficulty for simulate or modeling flow structure interaction problem by a mesh method. So certainly, as people would like to try the chance for a meshless method, because meshless method have a benefit that you are not strongly rely on the mesh anymore, and you are more free to choose use particles to cope with complex problem with large deformation or a topology change. So usually people will try to simple approach. So simple approach is basically they can introduce some simple coupling, especially the so-called heterogeneous coupling, which means they couple with SPH method with other type of numerical approach to cope with FSI problem. For example, you can couple SPH with DEM method or Lattice-Boltzmann method or finite element methods. So this type of method is very simple because you don't need to develop very specific approach. You can combine two already existing method or software to do this coupling. But this type of heterogeneous coupling face also very critical difficulties, because for those two different methods, when they couple to each other, very often they are not easy to satisfy the physical conservation laws, especially the conservation of momentum. And due to this lack of conservation of momentum, and they were also prone to introduce numerical stability. And also, not only numerical instability, very often they may lead to conversion to wrong values, because we need conservation to let the solution of a fluid dynamic or solid dynamic problem as a weak solution, because this weak solution condition require the system is conservative. So as we do SPH, so we also certainly will think about it if we are able to use the SPH itself only to model this flow structure interaction problem, because as we know, the SPH method is so flexible, and they don't need to rely on mesh, and that means we may able to model the fluid and the structure in within the same unified formulation. So people really tried. So in early modeling of FSI problem with SPH method is doing like this way. So what they do, I think is the first paper on this is in 2007. What people do is they extend the formulation of fluid to introduce extra property to simulate the structure. So that in this case, the fluid and the structure basically use almost exactly the same operator, like as in the Daniel's lecture, how to do the operator for gradient, operator for divergence. They can use the same operator for both fluid and the solid. What they need to do is, except they introduce some new factors to this equation, but this new factors is not so fundamental. So what they do is they introduce a Cauchy stress into the momentum equation to replace the pressure, which we usually used for fluid dynamics. So by this way, they introduce an extra stress tensor, so the so-called deviatoric stress tensor, which describes the incompressible part of stress, which is introduced by deformation. And this stress also go together with our evolution equation based on so-called Yeoman formulation for this. Then you solve the equation just like solving fluid equation, except you use the Cauchy stress tensor and introduce a special evolution equation for this dielectric stress. So in this case, you are able to simulate at the same time, use the same discretization operators for solid and fluid. So by this, so that will lead to the so-called the early stage of FSI modeling with SPH method. But people find this method is quite good. Very often they can simulate a very FSI problem with very good result. The issue they face is so-called artifacts on particle distribution. So when you do a flow structure interaction problem, very often your initial condition, especially for structure, the particles are in quite good order. And with time goes on, and with this type of simulation, and you can find the issue is the particles initially very well-organized uniform distribution of particle will go to some kind of noisy distribution. And this is not very serious if you do this for fluid simulation, because fluid don't have this so-called initial configuration with involving with solid deformation. But it's solid because we know for elastic solid dynamics, all the dynamics is based on the deformation referred to the initial condition or initial configurations. And if we use this Yeoman formulation or the fluid-like discretization, we need every time we need to evaluate the kernel values like the W and the derivative of W's at every time step, just like the fluid. This we can call it a so-called Eulerian kernel evaluation. By this way, we not able to remember the initial configuration of the system, of the particle, of the structures. So that means with time goes on, especially when your physical time is long and you have a back and forth motion for the solid, especially for the elastic dynamic solid problems, then you very often lead to artifacts of the particle distribution. So that means with time goes on, the particle lost its initial configuration. And when you have a long time simulation, very often they lead to a numerical instability again. So that means if we want to use SPH method to simulate FS problem, we can not directly use the very straightforward approach like the fluid-like approach. So that's why many people try to only use SPH for fluid, but they use an element or other method for the solid. But as I said, the heterogeneous is not a good option for full coupling dynamics. So people still try to use pure SPH method for that. For that, people later find if they use a different way to model the solid dynamics, they can got a very good result for the solid dynamics. This is so-called total Lagrangian formulation. This total Lagrangian formulation is they do exact as the finite element approach. They build the equation, every equation built from the initial undeformed configuration. So in this case, that means they only evaluate the kernel at the initial condition only once, then later keep this unchanged. In this case, they can keep the particle distribution for the elastic solid very well defined. Then they will not go noisy, and if you have on-loading, then all the initial particles will go to the initial undeformed formulation. That means they still remember everything. And this also introduces a lot of benefit. For example, this type of method is also free of tensor instability. When negative pressure or tensor is in the solid, and also as the kernel is only evaluated one time, so you don't need to update anymore. So basically, they will lead to very fast simulation of the solid dynamics. And also, as you maybe already know, for fluid dynamics, if you update the kernel function every time step, with time goes on, as a particle, their topology changes so much, and the memory distribution of this particle data would be very bad. So you need to sorting that to increase the performance. But for solid dynamics, if you use a total Lagrangian formulation, you basically don't have these issues. Oh, so that's the case. So if we want a model this fluid structure interaction, I would like to use a total Lagrangian formulation for the solid, and we try to combine, use the Lagrangian. That means Lagrangian kernel and Eulerian kernel combined together, and then couple the fluid dynamic and the solid dynamics in a conservative formulation, because we use the same SPH formulations. So here, basically, I show the governing equation. That's the same one as you already see. And I would like to mention is we also use weakly compressible formulation for incompressible flow, because we find this can be much faster than use pure incompressible formulation. And for the solid dynamics, then as we use total Lagrangian, so we build the kinematics. That means the displacement and the deformation based on the initial configuration, and we use this Euler-Lagrangian this deformation tensor basically only rely on the initial gradient operator with corresponding initial configuration. And in this case, if we use Tato Lagrangian, then the momentum equation or equation of motion would given only rely on the gradient operator evaluated at the initial configuration and a so-called first Piola Kirchhoff stress tensor. And this stress tensor can be related with the second Piola Kirchhoff stress and with elastic constitutive relation. And actually can be you can use very complex one like hyper elastic formulation material or elastic plastic material. They can all use this type of formulation and make this very flexible. And for fluid and structure coupling, we need introduce this coupling condition. So basically, if you have a fluid particles and the solid particles, like fluid particles on this side and solid particle on this side, and we also need to define the normal direction of the solid surface. And with those data, we can impose so-called kinematic condition. That means for the interface between solid and the fluid, the solid particle will determine the fluid structure interface position. So how the interface move is defined by the solid particles. And we also introduce so-called dynamic condition. That means how dynamics interaction happens near the interface. So first, for the fluid side, we need to apply the no-slip boundary condition, which near the fluid particle, or for the fluid particle near the interface. And we also introduce the fluidic force, like pressure force and the viscous force acting on the solid particles. So in this way, we can couple these two systems. After we decide this equation and the coupling, then we can discretize the equation. So this here is the discretization for the fluid. Is very similar as the first lecture already shown. The difference is here we have two extra terms represent the pressure force and the viscous force due to the presence of a solid structure. So this we need to have extra force when those particles is near the fluid and the structure interface. And certainly we can also use other formulations for fluid dynamics also. And for the solid, so in solid formulation, beside use this Lagrangian kernel, which we only calculate this kernel one time, and we also need to introduce a correcting matrix, which can reproduce a rotation of the rigid body, because we know rigid body rotation will not introduce any deformation. With this correction, and we can recover this rigid rotation. Then we can discretize the equation with the introduce of the so-called first Kirchhoff stress. And also here we have this extra terms. If the particles is near the interface, we need to consider the fluid pressure and the fluid viscosity acting on the solid surface. With this, then we can formulate the interaction force between the solid particle and the fluid particle. And this, we introduce a so-called conservative coupling. So basically, the coupling is based on pair force interaction way. So all the force can have a force and the reverse force, and they will cancel each other. And if you sum it all the force together, you got 0. And by impose the boundary condition. So the boundary condition is the slow slip boundary condition and the pressure boundary condition. If there's no gravity and no acceleration for the solid, then it's simply von Neumann boundary condition. When you have influence of gravity and solid acceleration, you have extra terms to take in account of that. So by this way, then you can discretize this equation, and then you will choose time stepping, because when to time step, you need to choose a time step criteria In this case, we need to choose the minimal time step criteria from solid and for fluid. Then we choose smaller, the minimum one of them, then you do the time integration. And certainly if we choose this way, then we'll have some computational issues, because when the sound speed very often is much larger than the artificial sound speed used in the water, then you will have loss of computational efficiency. Okay, so as I don't have much time to this, okay, if you want to go to detail of the formulation, you can check the code which we can provide on GitHub. And this now I would like to show some results. And here it's basically we just use total Lagrangian to simulate a pure fluid dynamic, pure solid dynamic problem, and you can check the convergence and the oscillation bin problems. And we can also model the structure, this so-called elastic plate or elastic dam problem, a breaking dam problem, and you can have the elastic gate. This one's rigid and the elastic, and you release, and then you got the simulation result. And you can see with total Lagrangian, you got very well distribution of particles when the solid is deformed. So you got a very stable solution and a very good result. So this is a comparison with the experiment, and if you do the simulation. And also here I'd like to show another test case. You have a solid and rigid body, so elastic body, solid, and fluid and rigid wall. And you can do this flow-induced vibration of an elastic beam behind the cylinder. So by use pure only SPH, then you can simulate this problem. And here this stress distribution is very well defined, and the particles are very ordered. And this we can measure there's frequency and to compare with experimental and previous result, and we got a very good result. And now I basically can conclude for this basic formulation. I would like to mention is if we want to simulate a fluid structure interaction problem, especially when you are using elastic solid and interacting with the fluid. I would strongly suggest to use this total Lagrangian formulation, which they are able to have very good numerical property, and we will obtain very good particle distribution. And if we cope with the coupling between the solid and fluid by pair particle interaction approach, then the strictly momentum conservation can be achieved, and numerical stability is very good. And I think that's the very good benefit of using total Lagrangian method. Certainly, there's still an important issue with this basic formulation for FSI. One of the most important issue is the computational time efficiency, because if we use minimal time step, which a criteria obtained from the solid and structure and the fluid, very often we will lead to very non-efficient simulation, especially when the solid part have very stiff material. For example, you have a liquid coupling together with metals like aluminum or copper. In that case, the sound speed in the solid structure are so high that your computational time, with most of the time, is wasted to simulate the solid dynamics. But at the same time, as you have the same time step, then you also waste the same time for the fluid simulation. Very often, fluid simulation is very costly. As I said, they need to sort in the particle, they need to evaluate the kernels every time step. So those are very inconvenient or very awkward when people do this fluid structure interaction. So we need to solve this problem by advanced approach. That's I will give you the second part of the lecture. I will show you how to do this multi-resolution SPH modeling for FSI problem. So, okay, that's my talk. Thank you.
Thanks very much, Hu. We now may take a break. See, there was a pressing question on the chat, and saying there was this velocity defined as twice VI minus VA, and next suggests perhaps it's 2 VI minus 2 VA minus VI.
Okay.
Could be a typo. I think he's
okay. Probably there's a typo there. Yeah, it's possible. It's possible.
I think
it's
so.
Possible. Yeah, because we need consistency is happened when the velocity of the solid is 0. And just got a negative value. Yeah. So let me check.
Ooh. Yeah, I think.
Yeah. The A is solid. This A. This should be the fluid velocity. The I should be solid particle velocity. So in that make this make sense.
Yes,
okay.
That makes sense.
Okay.
This is another question: whether it's possible to model free moving solid particles, such as colloidal particles. I guess he means like dust.
Depends how you try to modeling. If you want to model a detailed situation, then you need a multiple particle for one colloid. So then you can do like this. Then you can use exactly the same formulation as we showed here.
Yeah, that's an interesting topic. Yes.
If you want to have a less detailed colloid, for example, you just don't mind the colloid shape, then you just use one particle to represent colloids.
Yes, that's been done.
Okay.
Okay, thanks very much. Let's take a break and meet again in 15 minutes.
Okay, good. Thank you.
Okay.
Okay, welcome back. So let's go to the second part of the lecture. I would like to introduce a little bit more advanced approach, this so-called multi-resolution method for modeling flow structure interaction by SPH method. So the outline is like this. I first to briefly review this the traditional single spatial temporal resolution, and basically the uniform particle spacing used for both for fluid and solid. And we will use a single time step size for the time integration, which is the smallest of those required by fluid and solid structure. So, and I would like to review a little bit on the computational efficiency and the challenges for multi-resolution modeling. And then I will give the detail of the multi-resolution SPH modeling, which including the discretization with different spatial and temporal resolutions. And also, in order to address the challenge for the multi-resolution modeling, I would like to show a special position-based time integration method. And after that, I will give briefly numeric examples and the outlooks for further multi-resolution SPH modeling development. Okay, so the motivation of using multi-resolution flow structure interaction is basically due to the efficiency issue, because very often we may need a more accurate geometry structure of the structure. That means we may need a locally refined resolution for the structure. And sometimes the structure is quite relatively thin, and we also need a smaller particle size. And sometimes when the Poisson ratio of the solid structure is high, where it's close to 0.5, then incompressibility lead to very high bulk modulus and sound speed, which lead to a very small time step size for the solid. In this case, if we use a smaller time step for both, then we waste a lot of time on the computation for fluids, because fluids, in this case, they don't need so small time step. But then in this case, we would like to introduce a multi-resolution modeling. That means we hope we can use different particle spacing for solid and structure. And but for this case, we need to consider when you introduce a jumping of resolution, then sometimes the consistency issue will happen, especially when they cross the resolution jump. And then if we want to further increase the efficiency, we need use so-called multi-time stepping approach for the time integration. In this case, we find that if we use still the original wallet type of time step approach, then we may are not able to fulfill the conservation, momentum conservation property. And also, when you have different time steps for solid and fluid, their updating for force is not in the same frequency. That means when you have an interaction between the two, then you need to find a way to match these two different frequency force into one uniform interaction framework. So we need to solve those challenges. So what we would like to propose is we want use a uniform resolution for individual fluid and solid bodies, because this is the simplest case. That means we use one resolution for fluid, another resolution for solid. And but for solid, we assume we will have higher resolution. And this is in the case applicable when lower resolution is sufficient for the fluid part. In this case, if we want to save some time for the time stepping, I would like to introduce a nested time integration approach. If we together with some special time stepping approach, like the dual time step criteria SPH method, then we may have more complex nesting of time integration steps. Certainly, we hope that conservation is strictly imposed because of numerical stability and convergence property. And we also would like to cope with force matching problems. So let's have a look what we can do for this discretization. The first case is what's the step is simple. We just simply use different smoothing lengths for the solid and for fluid. So for example, we use larger smoothing lengths, and together that means small particle spacing when we discretize the momentum equation for the pressure term, for the viscous term, and also for the interaction force term. So we both use smooth length for fluid. But when we introduce in dynamics for solid, when we discretize the stress as acceleration, then we use solid smoothing length. In this case, the smoothing length is smaller than the one used for fluid. So this is the same formulation as before. The only thing we use smaller smoothing length and the particle spacing. But we need use the same and large smoothing length for the interacting force. Basically, this force is viscous force and pressure force. They are also fluidic force. So we also use a smooth length for the fluid. Okay, so in this case, but as we say, we have a different resolution. Then you have a different resolution jump between the liquid, the fluid, and the solid. In this case, we need to cope with this resolution jump. Especially this issues happens when you evaluate the density for the fluid. And if we use evolution equation for the density, then this the one showed in the first lecture, and we will use this symmetric formulation. And in this case, you consider the volume of particle I, that's neighboring particles. And for a fluid particle, the neighboring particle can be solid particles. In this case, the solid particle have a smaller particle spacing. That means have a smaller particle size. So in this case, they'll introduce small different particle volumes. So in this case, this is quite straightforward. Do not do many changes. The other thing is if we use some other special approach like the dual time criteria SPH method. In that method, we introduce another time criteria which is similar like incompressible SPH. That one is very large time step. And in that case, we need to introduce a so-called density initialization approach. In this case, when we introduce different particle size, then we need to use a special treatment for the initialization for the density to take in account that the particle size for fluid and solid, they are different. By this way, we can obtain smooth density evaluation near the fluid and solid structure interface. So by this way, and we can do for the density, and then for time stepping, what we can do is we can do the multi-time stepping approach. That means we have a different loop range. So if we consider we use a dual time stepping SPH method, that means we introduce actual time step criteria based on the advection speed of the particle, like the incompressible SPH. Then we were made one outer loop. That means this loop with the largest time step. Then below that, we will also have the so-called middle loop. This middle loop is come from the time step criteria of the fluid acoustic criteria, which is less than that of this advection criteria. And below that, we have the minimum time step size for the inner loop, which is from the solid acoustic criterion, which is dominated by the speed of the sound in solid. And for this dual time stepping SPH method, the advection time step criteria is control the frequency for updating fluid neighbor particles. So as we know, as we use total Lagrangian formulation for the solid, we don't need to update the neighbors for solid particles, but we need to update the neighbor particle between the solid and the fluid. So in that case, we still need to update the neighboring particles. And for the middle loop and the inner loop, we use this two loops to solve the momentum conservation equations and the density evaluation. So this is the middle and the inner loop. So there's these three different loops that we can nest the three loops together to achieve a so-called multi-time stepping integration. Okay, so but if we use different time step and nest this time step, very often we may have issues of strictly conservation of the momentum. So I'd like to show you one example. If we assume that we have one acoustic fluid acoustic criteria time step, then we will have four solid time step. So this case, then you have a ratio, time step ratio is 1 to 4. And then we show if we use original, the velocity-based volet or the kick drift the approach for solid dynamics, which they update the position one time and update the velocity 2 times. One time is half time step velocities. So this is volet method. And if this one is for fluid, so we update 1 step position and two half step for velocity. And if we use the same algorithm for the solid, then you will have a situation like this. You will update the space 4 times and the solid like this. The only thing is not exactly 4 times for the solid because for the velocity, because as there's a 2 half time step, which is in front of this loop and behind this loop. And make this momentum conservation, which is related with update of velocity, is not strictly conserved. So to achieve a strictly conserved momentum conservation, we need to modify the velocity-based volet algorithm by position-based velocity. In this case, we update the position by 2 half-time steps, but update the velocity in 1 time step. And in the case, then we switch the relation for position and velocity update, in this case, between fluid and the solid. In this case, and the solid is more like exact 4 times for the velocity. For the solid, the velocity is updated exact 4 times, which is exact corresponding to the time instant for the fluid updating. And then we have introduced one head and tail for the position update. As the position, there's no conservation law there to be strictly conserved. Then we can say we want to use the strictly conserved momentum to do this updating. In this case, we can strictly conserve the momentum between the fluid and the solid. Otherwise, we are not able to conserve strictly. So by this way, then we are able to achieve very good numerical stability. So now we need to have a force matching. Oh, that means before there's something wrong. There's a typo. This should be 2 times this A and 1 time this V. Yeah, this is really a typo. Okay, so in this case, we need to have a force matching between fluid and solid, because as we know, for 1 fluid time step, we only update the velocity 1 time. But for the solid, for the same time period, we update the solid 4 times. So which update for velocity would be used for interaction, for the interaction term? What we do is we introduce a solid and fluid boundary condition based on the averaged velocity for the particles, for the solid particles. So we average the acceleration from the solid particle, and at the same time we average the velocity from the same particle. So here, as I say, there's a typo there. So it should be not this. This should be here. Yeah, by this way, when we calculate the interacting terms, we basically, the velocity of a fluid and a solid, they basically mean the velocity for the same time period. Then we can solve the problem of this force matching. So by this, then you can, I show you this, basically the algorithm, there's 3 different loops. You can see the outer loop, which is for the advection criteria. Then with the middle loop, we do this acoustic criteria for fluid, and then the inner loop, we do the time step for the solid. And by this loop, we use position-based velocity approach to make the conservation of momentum can be strictly conserved. Okay, so that's the algorithm. So if you have interest to look at the detailed algorithm, you can also check the repository for the code, and there's examples which solid dynamic FSI problems, and you can check how it exactly implement for multi-resolution method approach. Here, I'd like to show some examples. So if you have this example, then you can use it to simulate some special case, which is very hard for single resolution approach. The first case is so-called hydraulic water column on an elastic plate. So you have water column, and you have an aluminum plate, which will very high sound speed. And then you want to obtain deformation of the aluminum plate if under the action of the water. And here I choose different cases with different resolution ratio. So for ratio 1, that means same resolution. If ratio higher than 1, that means solid have higher resolution. So ratio than 4, that means is the highest situation. And here we consider the situation with the same resolution for the solid. That means all cases at the solid wall, there's a plate, we have 8 particles along the surface. And we try to use different time stepping approach. We can also use single time stepping and multiple time stepping. And you keep in mind, this single time stepping is also for multi-resolution. So we may have a very extreme situation, use a single time stepping and same resolution for solid and fluid. And this, we didn't show the case here because, as you can imagine, in that case, would be extremely slow. And here it gives the number of particles, and we show the result. And you can see this is the middle span of displacement of the elastic plate at a constant solid resolution, but with increasing resolution of the I think it's of the fluid by introduce different resolution ratio. So when you have a higher resolution for fluid, you have a low resolution ratio. When you have a small low resolution for fluid, then you got a higher. Then you can see the simulation result give approximately the same displacement, because this is because the resolution for solid is exactly the same. And you can find the simulation is very stable, and they are approaching to a very what should I say, equilibrium state with very small with accurate value. And also we can also use different fluid spatial with fixed fluid spatial resolution, but with different resolution ratio. And you can find when you increase resolution ratio, that means with same fluid space resolution, but the higher solid resolution, you got a very good convergence. And also if both resolution is increased, you also got a very good convergence. And keep in mind, this resolution you can see is high order. It's not first order resolution as we usually obtain for SPH. This is higher than second order. I think probably second order, it's clear. And also this energy decay, you can find the simulation is very stable and they will not lead to trouble. And also here they give the CPU time for the same computer, and you can find when you use high resolution, you can space resolution ratio, you got very fast simulation and very yeah. But if you compare this one with a single resolution and single time step, then the speed up is extremely high. For example, for the resolution ratio is 2, you got 240 times speed up, and your resolution ratio is 4, you got nearly 1,000 times speed up. That is extremely high speed up. And use the same approach, you can do other simulation. For example, for the elastic dam break problem, then you can also show that if you use multi-resolution, you decrease the time step, you decrease the simulation time very much. So you can see if you use multiple time step and high resolution, then you only got a very small time step, very small time for the simulation compared to very large simulation times. And similar case can be found for the flow-induced operation of elastic beam behind the cylinder, and you can find the simulation time with multi-resolution can be very small compared to very large value. If you don't use multi-resolution, then the speed up is very great. Okay, so as you have this multiple resolution, then you will be easily to simulate structures with thin structures in the flow. For example, here we consider a vine, ideal is the vine with flexible valve leaflets. So the valve leaflet is very slim compared to the fluid particles. Then you can simulate because you can introduce high resolution for the two valves and obtain the flow structure. When the flow simulation don't need very high resolution, then in this case we can get accurate simulation for the solid part, because in that case the solid may need to require higher resolution for this case. And we can also introduce similar things when they do other more complex flow structure interaction. Here is one case you teetered one fish body type of structure, and put this one into a flow, then this fish type structure will flux and flapping produce vortex in the flow. And in this case, because you can use quite accurate fish model, because as you see, the fish tail need a very thin has quite thin. So in this case, you can use smaller particle to model this fish-like structure and use even more particle for the fluid. Then you are able to obtain quite accurate result for the fluid structure interaction problem, which is very important if you need refined structure there. Okay, so that's the example. And here I basically show you that we can use different resolution. That means different resolution for fluid and structure. And if you can cope with this momentum conservation issue where, and if you can consider cope with this resolution jump consistency issues, for example, density evaluation, then you can introduce multi-resolution method for this type of problem very easily. And they were also got a very good result for this. And actually, the multi-resolution the idea not only can be used for fluid structure interaction. For example, if you have two different fluid, you can also, like different fluid, have different resolutions. For example, here I would like to show the example which we did for when you consider. This cannot show. Or... Hey, this. Oh, it's because this one is not. Let me. Let me this discount, and then I would like to show again. Hey, cannot. So we can.
Yeah, I think they might work now. I mean,
why is it not working? Surprise.
Preview. There was a preview option, and I think that tends to work.
Preview.
Preview, yes, I think. I'm not using PowerPoint so much, but.
Okay. But it's okay. But actually, I can go to YouTube as actually on YouTube, so it's not so
okay.
difficult. Which this case is then you can use a difference resolution for two different fluid, and when you have a complex situation, you have fluid and structure and different fluid resolutions. You can have a so. No, our code is not like this, so it's yeah. This I will show this problem. I would like to show you is this. Yeah, this one. So in this case, you have two a fluid, but you have you see you begin this dam break. You have a air particle, low resolution, high resolution for the liquid particle, and high resolution for the wall particle. Then you can introduce the same idea when you use different resolution. If you cope with density jump or a smooth length jump and conservation issue where, then you're able to simulate the problem with very different resolution. So here you can consider the case when you have a different fluid and different fluid with different resolutions. Because in this case, dam break, the splashing is more important than the air motion, then you can use a high resolution for the liquid and low resolution for the air. And this is a case for that. You can also show, I can also show another case when you have even more complex case. Here is a case with ocean driven wave. Then you have a high resolution for the low resolution for the air, high resolution for the liquid, and still even higher resolution for the structure. Then you can use you can simulate the problem with the multi-resolution idea. But importantly, you need to cope with the issue of resolution jump, consistency, introduce consistency, and momentum conservation introduced at the boundary interface. Okay, so that's the example I'd like to show to you. And basically, I should close it. Okay, so this is my outlook, and I'm happy to answer your questions. And certainly, I would answer the question left over for the first part of the lecture.
Mhm.